How contaminants move in southeast Minnesota groundwater.
Understanding how groundwater moves in southeast Minnesota is key to understanding how contaminants can enter groundwater. Most contaminants found in the region's streams, rivers, and drinking water are a result of human activity on the land surface.
A tractor is pulling a sprayer in a row crop field and is applying pesticides.
Some commonly detected contaminants include bacteria, pesticides, fertilizers, and chloride.
A truck is applying salt to a highway in the winter.
These contaminants can enter aquifers, where they might move at many different speeds and across great distances.
An exposed rock quarry face is shown. There are a variety of horizontal and vertical cracks. Animation is added to illustrate the movement of water from the surface through these cracks known as conduits and fractures. The water turns from a blue color to a lime green color, indicating contamination from the surface. There is a small stream flowing over rocks, and then aerial footage of a vast agricultural landscape, including bare farm fields and windmills.
One of the most mobile contaminants found in Minnesota groundwater is a form of nitrogen called nitrate. Although nitrate is an essential nutrient, excess sources primarily come from fertilizer, animal manure, and human waste. In southeast Minnesota, where the landscape is less populated, nitrate largely comes from cultivated cropland. Let's examine how nitrate can move into drinking water and surface water across 3 unique landscapes in southeast Minnesota.
These 3 landscapes are shown from west to east as glacial till, karst, and bluffland karst. These landscapes extend across an 8-county area. The boundary of the Root River watershed is also shown. The watershed boundary intersects with Dodge, Olmsted, Winona, Mower, Fillmore, and Houston counties.
In the glacial till landscape, karst aquifers are present below the glacial sediments, but nitrate is less likely to reach these aquifers.
An illustration is shown that shows the cross-section of the flat glacial till landscape. The first layer is comprised of the glacial till layer. A scale bar shows its thickness is up to 200 feet thick. Below that lies alternating layers of limestone and shale. The limestone has cracks and fractures. The top of the water table is about 50 feet below the land surface. A shallow well and deep well are displayed. Flat agricultural fields containing corn and soybeans, 2 homesteads, and a drainage ditch are shown on the land surface.
This is because the thick layer of clay-rich glacial till acts like a barrier and provides some protection to deeply buried aquifers below. Additionally, most water soaking into the ground is captured by a network of drainage tile.
An aerial view of a cornfield shows a network of underground drainage pipes. These pipes connect together and flow into one pipe that empties into a drainage ditch
that flows directly to surface water ditches and streams. Although these factors create less risk to drinking water here, nitrate moves downstream in creeks and rivers to the karst and bluffland landscapes.
A map illustrates how water from the headwaters travels from west to east through the different landscapes, discharging into the Mississippi River,
where it can move quickly into the bedrock and mix with groundwater. In karst, nitrate can travel to both surface water and drinking water by moving rapidly through shallow soils and into the underlying fractured bedrock. Unlike the till landscape, dense layers of clay are no longer present. This means that the soil's ability to naturally filter potential contaminants is reduced.
A view of the karst landscape cross-section is shown again. As surface water travels down through the land surface, the water becomes contaminated and flows quickly through the vertical and horizontal cracks. Most of the contaminated water is above the shale layer. Once it reaches the shale, it flows horizontally where it emerges out of a spring. This same water then flows to a stream.
Leaching, or downward movement of nitrate through the soil, is the primary way nitrate is lost to groundwater. Leaching occurs on all cropland acres throughout the region. Since nitrate dissolves in water, it follows the same path groundwater takes through the bedrock and can eventually end up in a drinking water well, spring, stream, or river. although sinkholes are an important and visible feature in karst.
A series of sinkholes, or large depressions, dot a farm field. Trees are growing in the sinkholes, making them easy to see in the agricultural field.
They are a minor pathway for nitrate to enter groundwater. However, after a snowmelt or a heavy rain event, overland runoff into sinkholes can provide a direct connection for contaminants to enter groundwater and surface water.
The karst landscape illustration is shown again. Water movement arrows show surface runoff flowing into a sinkhole. This contaminated water flows through a fracture under the sinkhole, which then intersects with a shallow drinking water well, and then emerges from a spring. This water then flows to a stream.
The movement of groundwater to drinking water wells in karst can be difficult to predict. But in general, layers of shale can help slow nitrate from reaching older, deeper groundwater. Results from drinking water monitoring in this landscape have shown that higher nitrate concentrations are usually highest in groundwater that's closer to the surface, while lower concentrations are found in deeper wells that pump groundwater from below protective shale layers. Although well depth is a key factor affecting nitrate risk to drinking water, well construction and maintenance is also important.
A cross-section of the soil shows a well with casing and a drop pipe within the casing. Water movement arrows show that the water is being pumped up vertically. The well is grouted on both sides, which seals the gap between the well borehole and the casing.
Wells not properly maintained or constructed using modern well drilling techniques are more vulnerable to contamination.
The same cross-section and well is used, but this time the well does not have grout.
For instance, over time, well casing may corrode or crack, allowing water to enter the well near the land surface before contaminants can be filtered out by the soil. Casing also plays an important role in determining which area of the aquifer a well draws water from.
Two wells are shown, a poorly constructed well on the left and a properly constructed well on the right. In this example, the casing on the poorly constructed well is much shorter. Contaminants near the surface reach the base of the casing much more quickly and are drawn up the well. The well on the right has deeper casing, extending into deeper bedrock layers. This well draws groundwater that has less connections to the land surface.
When comparing two wells at the same depth, the well with shorter casing may have much different water quality, even though they are right next to each other. Similarly, grouting is intended to fill any gaps between the casing and surrounding bedrock.
The grouting for the well on the left has changed. It is now poorly grouted and a gap exists between the grouting and the casing.
A poorly grouted well may allow water from the land surface to run down the sides of the well casing and directly into the well. This can help explain why a deeper, poorly constructed well might have higher nitrate compared to a shallower, properly constructed well. In the bluffland karst landscape,
An animated cross-section of a bluffland karst landscape shows a deep valley surrounded by tall bluffs on either side. The valley is wide, with a flat floodplain that includes agricultural and forested land and a stream. The bluff walls are steep and have exposed bedrock outcrops. The bedrock is composed of alternating layers of limestone above a layer of shale. The lowermost rock layer is sandstone.
the upward flow of older and deeper regional groundwater affects the concentrations of nitrate.
The video zooms in on the animated cross-section, focusing in on the base of the valley and stream. Groundwater forced upward mixes with water near the surface and in the stream.
Older groundwater that can be several centuries old mixes with younger water that has higher nitrate. This mixing process reduces and dilutes nitrate in bluffland streams and some aquifers. As it relates to drinking water, shallow wells are just as susceptible to nitrate contamination in the bluffland setting as in the karst landscape. Despite nitrate dilution from mixing of older groundwater, nitrate can still move to deeper aquifers, slowly increasing in concentration over time. Long-term water monitoring has shown that nitrate concentrations are increasing in groundwater flowing to bluffland streams. This rate of increase is about 3% per year.
A chart is displayed that shows the nitrate concentration in Bridge Creek, which is located in Houston County. The years 2010 through 2020 are shown on the x-axis, and on the y-axis, the nitrate concentrations in milligrams per liter are displayed. Over 1,200 data points are shown. Most of the values range from 3 to 5 milligrams per liter. A trend line is drawn, illustrating a slow but gradual, statistically significant increase over time.
This does not necessarily mean that nitrogen sources from the land surface are increasing at this same rate, just that nitrate leached today, or yesterday, or 40 years ago have not fully made their way into deeper groundwater. This delayed response, called lag time, is also occurring in some deeper drinking water wells, where nitrate concentrations are slowly increasing at a similar rate.
There is an aerial view of blufflands, farm fields, farmsteads, and roads.
Over the past several decades, communities in southeast Minnesota have taken important steps to protect groundwater. Many farmers are using more efficient management practices on cropland.
A close-up view of a person's hand using a touchscreen monitor in a tractor. This technology helps farmers apply nitrogen fertilizer more precisely.
Rural homeowners are sealing abandoned wells, fixing leaky septic systems, and landowners are keeping sinkholes free of trash. Despite these efforts, ensuring clean water for future generations will be an ongoing challenge, and additional efforts and focus will be needed to reach our clean water goals and standards.
An aerial view of a road following the base of a bluff with agricultural land, forested land, and the river off in the distance.
The next time you drive through the area, consider how easily actions at the land surface can impact groundwater. Then continue to think about what you can do to protect this vital resource for everyone to enjoy.
The credit screen includes the following information. Video production by Minnesota Department of Agriculture 2020. Advising organizations include the University of Minnesota, Minnesota Geological Survey, Minnesota Department of Natural Resources, Minnesota Department of Health, University of Minnesota, Minnesota Extension, Minnesota Pollution Control Agency, Minnesota Ag Water Resources Center, Olmsted Soil and Water Conservation District. Produced by Kevin Keener. Animation and video production by Luke Porter, Moving Tree Media. Written by Kevin Keener, Bob Tipping, Julia Steenberg, and John Barry. Editing, review, and support by Jen Schaust, Britt Gangness, Greg Klinger, Anthony Runkle, Jeff Green, Yaba Kiersgaard, Margaret Wagner, Martin Larson, Emily Zanin, Kim and Barbara Crawford, Justin Watkins, Dr. Calvin Alexander, Kent and Jude Dornink, Warren Formo, and Kevin Masarek. Funding sources include Minnesota's Clean Water Fund through the Minnesota Department of Agriculture's Root River Field to Stream Partnership, Minnesota Pollution Control Agency, and a grant from the Minnesota Corn Research and Promotion Council. Trout fishing footage courtesy of Trout Unlimited. Special thanks to the Minnesota Geological Survey for their assistance with this project.